Welcome everyone to this One World Mathematical Physics seminar of IAMP. And today it's my great pleasure to welcome Antti Knowles, who's going to talk about the Euclidean 542 theory as a limit of the interacting Bose gas. And I just want to remind you that this talk is being recorded and you can then watch it on our YouTube channel. So please, Antti, go ahead from here.
Thank you. And thank you very much also for this invitation and opportunity. So I will talk about some recent work that I've been doing with Jürg Fröhlich, Benjamin Schlein, and Vedran Sohinger on interacting quantum Bose gases and their relationship to Euclidean field theory. So I was asked to make this pedagogical. I'm not sure if I succeeded, but at least you should ask questions if anything is unclear. So I will start with some background on this Euclidean field theory, since not everyone might be completely familiar with this object and its history. So basically the idea is very simple. So you start with a torus and you would like to construct fields living on this torus. So I hope you can see my little hand. Can you see this hand? Yeah, okay. So I will always work on the torus. I'm not interested in the thermodynamic limit in this talk, although it is, of course, an interesting topic. So my fields, they will be complex valued. That's why I added this complex here. And formally, what you would like to do is to construct a probability measure of the following form. So you take an action, S of phi, which I will define in a minute, and you just define the Gibbs measure associated with this action, S of phi. Let's set, to simplify notation, let's set the temperature to be 1. You could absorb it into the action if you wish. This C is just a partition function, and the d phi is, well, is a somewhat delicate object. It's this uniform measure, or if you wish, Lebesgue measure on the space of all fields, which of course doesn't exist. But if you wish, and in fact, that's not a bad way to think of these things, you can discretize your torus, and then this makes perfect sense. And then you can try to take some kind of continuum limit. So this action consists of a free and an interacting part. The free action is just basically the Laplacian. So here it is. I choose the sign so that this is a positive operator. And I also add a mass term, which I call kappa, and this is just a positive constant. So this is my free action. And I have an interaction. In fact, you don't see it, but I have a window with all of your faces, which is of course very pleasant, but it hides a part of my screen. So let me put it over there. And the interaction is going to be this quartic term. So this is the origin of this phi to the 4. I take it just, you take the field at location X, and you take its 4th power and you integrate over that. So this formally, of course, this is not a mathematically well-defined thing as it is. There are lots of issues in particular here, but one would like to make sense of this thing mathematically, and the history of this. I think many of you know already about the history of this. It's a very, very interesting object, and it has seen a huge amount of attention in the past now 70 years, even in the mathematics community. And it does originate from high energy physics and this program of constructive field theory as the simplest non-trivial interacting field theory you can try to construct. From a physics point of view, it is in fact more important in solid state physics. It is supposed to be the scaling limit of various lattice models of statistical field theory at or near criticality. And in this talk, I will give a different interpretation of this field theory in terms of a different model of statistical mechanics. That's somehow the point. Before we get there, let me explain a bit how to make mathematics out of this. So, as I said, this is related to many areas, some of which are very active these days of mathematics. So there's this program of constructive field theory. I give a few names and dates. I will not go over them. You probably know some of these references. So this is how it started. Now, recently, there's been a huge amount of interest in this problem from in the community of stochastic PDEs. where you just take the Langevin equation associated with this action. So I mean, you know, if you have a potential S of phi, you can define the Gibbs measure, which is this mu. You can also define the Langevin equation by taking the gradient of this potential and adding white noise. So in this case, we are in infinite dimensions. So this psi t is white noise not only in time but also in space. And this gives you an equation which formally makes sense, and then you can try to make rigorous sense out of it. And this is not at all an easy question. And there's been a huge amount of activity in this direction. Formally, and this has also been proved under various assumptions and contexts, this measure mu is invariant under this stochastic PDE. Another direction which has also been very active is that of dispersive nonlinear PDEs. So you can also calculate that it is invariant for this deterministic nonlinear Schrödinger equation, which in fact you can see as a Hamiltonian equation of motion associated with this Hamiltonian. And these kinds of measures mu, they provide a very powerful tool to construct global and time solutions of very low regularity. As we'll see, these solutions, so these fields are typically extremely irregular objects. In fact, they are, unless you're in dimension one, they are not even functions. Okay, so can you still see my screen?
Yes.
Yes.
Yeah.
Okay. Good. So how does one construct this thing? So the difficulty of this construction increases very rapidly with the dimension. So let me explain the basic idea. So you start with the free field. So you set the interaction to be 0, and then it's easy. The free field is Gaussian, and we know how to construct Gaussians for basically any covariance at all. So the covariance you would like to have is this one. So this was if you recall, this was the quadratic form in the exponent. So this is my covariance, which I call G for a green function. So here it is. This is my green function. It's a complex field which has a gauge invariance. So I always calculate phi and phi bar. If I take the expectation of phi by gauge invariance, I get 0. And so if the interaction is absent, then I just take my measure mu to be this probability measure P, the Gaussian measure on this infinite dimensional space. So that's very easy. And the idea is to define the interacting theory as in terms of this free theory. So you add a Radon-Nikodym derivative, and you would like to make sense of this. Now in dimension 1, this works, and this is kind of trivial. It works for 2 important reasons. The first one is this interaction is positive, it has a sign, so this density is bounded. And secondly, this interaction is in L2 of this probability measure. You can do this as an easy exercise to figure out that this is in L2. This is just Wick's theorem. So take this interaction, apply Wick's theorem to it. So take it, square it. You have an integral over x and y. Then you have phi of x to the 4, phi of y to the 4. You take the expectation with respect to this Gaussian measure. You apply Wick's theorem, and you get just a power of g's, which are all bounded in 1D. The green function is bounded, and therefore this is in L2, and you can construct your field theory in 1D. It's very easy. I hope this was okay. So again, feel free to interrupt if something is unclear. It turns out as you increase D, things become much more complicated. So already in dimension 2, this fails. It fails because this is no longer in L2. You can try to do the same calculation. Now G has a logarithmic singularity and everything blows up. And in fact, you can analyze things a bit more carefully, and you will find that this phi is almost surely not a function. So for almost every realization of your probability measure P, this is a distribution, and it has negative regularity if any dimension higher than 1. So the solution is well known, at least a part of the solution, depending on your dimension, is well known, is you have to renormalize your interaction phi. So this phi somehow is too large, and you do that by subtracting infinities, infinite counter terms. And there's a simple systematic way of doing that, which is just to Wick order everything. So This is my notation for Wick ordering. So this is a polynomial in this Gaussian field, and these two dots mean I Wick order it. And just to recall, if this is no longer fresh in your mind, this is the definition of Wick ordering. So you can, I think this is a nice way of summarizing it. You take a general Gaussian vector with mean 0. So this is just a Gaussian vector, it can have an arbitrary covariance. Then the Wick ordering of this product of these n terms, some of them could be the same. I mean, you could take the nth power of a variable, is given by this generating function. If you didn't have the denominator here, you would just get the normal power of psi1, the normal product psi1 up to psi n. And the Wick ordering means you normalize this generating function with its expectation. That's it. So when you differentiate, you can either differentiate upstairs, which gives you powers of these x's, or you can differentiate downstairs, which will give you expectations of powers of xi. And this kind of neatly packages the whole algebra. So the Wick ordering here, you can calculate this as a little exercise, and this is what you get. So you get the original term, of course, but you get these two terms as well, and you can interpret them as a mass and energy renormalization. So this, if you see, there are lots of lines, but I hope you can see what's going on. So this is just phi squared, and it's multiplied by a constant, which happens to be the expectation of phi squared. So this is a renormalization in the mass, and this is just a constant, which is a renormalization in the energy. So now, if you read this, you will realize that this makes no sense, what I wrote, because this is not a function, so you can't take pointwise products, and similarly, these expectations are all infinite. Of course, it has to be, because we want to subtract infinite counter terms from this thing. So the way to do this properly is you regularize your field phi to begin with, you convolve it with some smooth approximate delta function. Then all of this makes sense. You calculate this Wick-ordered polynomial or monomial of the regularized field, and then you remove the truncation. You send your approximate delta function towards a real delta function, and you prove that this random variable converges. So this can be done. In fact, it's not hard at all. So again, if you are interested in these things, you can do this as an exercise to show that this thing is well defined. And then you get a Wick-ordered interaction. And this, in fact, it turns out to be sufficient in 2 dimensions. So now in 2D, you can prove that this Wick-ordered interaction is in L2. So I'm sorry, I used the same symbol as before. There will be many different objects in this talk, and I was unable to choose different symbols without creating some kind of an aura of indices around every single symbol. So this is now the Wick-ordered interaction. So you can prove it's in L2. But now you have to pay a price, which is quite steep, and it's that this thing is no longer positive. You see, when you Wick order, you lose the positivity because of this term here. And that's a problem, because you want to define the expectation of this, well, you want to compute the expectation of this exponential, and this is now an exponential of a thing that can be arbitrarily large in the exponential. However, it turns out that that this thing, although it is unbounded, it has very strong decay. So W has very strong decay towards minus infinity. There are some large deviation bounds due to Nelson, which you can derive and show that this exponential is integrable, although it's unbounded. This was a sort of a trailblazing paper of Nelson in the 70s to figure out how to do such things probabilistically. Now, if we go to dimension 3, again, things become increasingly difficult. And in particular, you can again do this calculation. Now, even after Wick ordering, this interaction is no longer in L2. The reason for that is you can just do that, but the reason is that G has an algebraic singularity, and you get terms which have a too high power of G, and they are not integrable. And you can do a formal perturbation theory, for example, for the 2-point function. I think that's the easiest way to understand what's going on. So you take the 2-point function of this field theory, you put in phi of x, maybe, yes, you put in phi of x times phi bar of y, you calculate the expectation, and you just do an expansion of this exponential. And you will see even at second order second order, you get terms which are infinite. So let alone being able to sum up the whole series. And this requires a further renormalization, which is a mass renormalization. So you have to subtract an extra counter term, which cancels these divergences. And it turns out that this is sufficient. But this is quite delicate. So there's a huge literature which goes up to the present day of trying to find ways, general and simple ways to construct these theories. I think simple, probably we are still not quite there. So it turns out all of the constructions of this 543 are somewhat complicated. And in dimensions 4 and above, things are very different. It turns out that there the singularities of the field are so strong, or the singularities of the interaction are so strong, that no matter the renormalization you pick, you can try to renormalize this interaction as you wish. If you choose a renormalization which gives rise to a well-defined limit, this is always going to be trivial. So the only way to tame this very singular interaction is to kill it, basically. So this is, in fact, a conjecture for the complex valued field. For dimensions 5 and above, this has been proven in the 80s by Fröhlich and Eisenman in independent works. And if you take your field to be real valued, then there's, in fact, very recently, a beautiful paper by Eisenman and Dominique Copin, where they prove this for 4 dimensions. But unfortunately, their proof relies quite heavily on the fact that your field is real. So for complex fields, this is almost certainly true, but not yet proved. Okay, so this was a short summary of this Euclidean field theory. Let me now move on to a completely different thing, which is I think is familiar to everyone, to the audience. Let me review my notations for the interacting Bose gas. So I will define bosons on this torus. Remember, lambda was my d-dimensional torus. So this is my space of n-body wave functions, which are bosonic, so symmetric in their arguments. And I will take the following Hamiltonian. So I didn't use creation and annihilation operators, partly to save time and space and partly to avoid having to introduce them. Of course, this thing would be most naturally written in terms of them. But this is also, I don't really need them much in this talk, or in fact, even in this whole work. So we can get away without them. So my Hamiltonian is a generic interacting Hamiltonian for n bosons. So I have my kinetic energy term. I have the same constant kappa. I have an interaction with an interaction potential V. I put in some constants, nu and lambda, which I will need to choose later on in various limiting regimes. And in addition, I put in some renormalization parameters. So I introduce a renormalization of the chemical potential. So if you multiply by the particle number, then you get the thing in front is the chemical potential. And I also take an energy renormalization, which I call beta. So then I define the grand canonical ensemble, which is just a sequence of these density matrices on n particle space. So my grand canonical partition function is going to be this sum, and the ensemble in the nth particle sector is just given by the following object. And I define the reduced density matrices, which, if you know these creation and annihilation operators, they will just be the expectation of a star of x1 up to a star of xn, and a of x tilde x1 up to a tilde of xn, a star of xn. But they can also be defined very explicitly in terms of these n particle density matrices as follows. Okay, so that's another way of defining these reduced density matrices, and this is the partial trace. So you sum over all n greater than p if you want to take the p particle density matrix, and you trace out all but p particles in every single one of these. Okay, so this is my quantum Bose gas, and what I would like to do is to relate these two theories to each other. So I would like to prove that in some appropriate limiting regime, this quantum Bose gas tends to a Euclidean field theory. So in terms of the convergence of the partition functions and reduced density matrices. So the partition functions themselves, they will not converge, what I'm always looking at is the relative partition function. So this was this partition function. I will divide it by the partition function of the free theory, so where you have no interactions. And this thing should converge to the partition function of the Euclidean field theory. So if you recall, I called that zeta. So here it is. So it's just the expectation of e to the minus w. And similarly, the reduced density matrices. So if I take this reduced density matrix gamma p, which was this object here, and I take some limit. So the limit is going to be that of mu tending to 0. So the limit is always going to be this guy. This is somehow the fundamental parameter. This will tend to 0. And if you wish, there are many ways of interpreting this limit. One, the most obvious one, is that you take the limit of a high temperature, since this multiplies the h in this Hamiltonian. By rescaling, there are different interpretations of also a fixed temperature and high density and so on. So this gamma p, after an appropriate rescaling, will converge to a quantity which is just the correlation function of my field theory. So these little gamma p's, I define them in terms of the operator kernels, and here they are. So this is something that I would like to prove in a variety of limiting regimes. Okay, so let me now give a few results in this direction. So these are previous results. So the simplest such limiting regime you can get is the mean field limit, where I choose my lambda to be nu squared. So I have a nu here and I put a nu squared here. I will not talk much about the alpha and the beta. They always have to be tuned in such a way as to obtain a non-trivial limit. The choices are explicit, they are unique up to a constant, and I will not dwell on them too much. I mean, you just have to choose them right, otherwise everything explodes or becomes free. And this mean field limit corresponds to a high density limit, and the interaction is proportional. The interaction strength is proportional to the inverse density. So it's very much a mean field limit. The range of the interaction remains of order 1 in a torus of fixed diameter. So every particle interacts with a macroscopic number of particles. And in that case, you do not get the Euclidean field theory I was talking about. You get a modified Euclidean field theory with a non-local interaction. So this quartic interaction is in fact going to be a non-local one, where you have two quadratic parts. This is the mass of the field at location x, and I apologize, there should be an x tilde on this one. Which is interacting with the mass of the field at the location x tilde via the interaction potential V. And I Wick order also, but I Wick order these two things individually. So this is just I'm just subtracting multiples of the mass and the energy in this Wick order. I could also omit it and then somehow introduce it by hand later if I wished. So this indeed turns out to be true. So the convergence to the mean field limit is true. That's in fact, there has been quite some work on this in the past 6 years now. It started with a paper of Levin, Nam, and Rougerie from 6 years ago, where they did the 1D case where no renormalization is required. Somewhat later, we gave an alternative proof in 1D, and we also gave an argument that works in 2 and 3D, provided you work with a slightly modified or regularized version of your grand canonical ensemble. The full 2D case was understood again by Levin, Nam, and Rougerie a bit later, and then last year the 3D case, okay, all dimensions 1, 2, and 3 were understood simultaneously in 2 independent works by us and also by Levin, Nam, and Rougerie. In fact, it's not just in the same year, the papers appeared on the same day on the archive. It's not entirely coincidental, but almost. And the proofs are extremely different. I will explain a bit how our proof goes, because what I will talk about today relies in part on this paper as well, relies on the methods of this paper. Okay, but we would like to understand how this Euclidean field theory with the local interaction arises, and also from a physically maybe somewhat more realistic limit where you don't have a mean field behavior, so you don't have all particles interacting basically with all other particles. And what you do, as you always do in this business, is you take an interaction potential which you scale down to a delta function. So I will introduce a parameter epsilon. I will not give too many technical assumptions or details. It's not so interesting, but you should think of this v epsilon as being you take your favorite smooth function. Actually, smoothness is not so important, but let's assume it's smooth. Let's say it's compactly supported. It has to be of positive type. That's important. So we need repulsive interactions. That's very important. It's easy to see that these field theories, they cannot make sense unless you have a repulsive interaction. And the range of this thing is epsilon. So you scale your potential in such a way that the range is of order epsilon. We will send epsilon to 0. And then the theorem that we proved this year is that in 2 dimensions, if you send all of these parameters to 0, so mu, this is this nu, this lambda, and simultaneously the range of the interaction potential, and you adjust alpha and beta as always appropriately, so you adjust the renormalization appropriately. With this still the same scaling, and we need a technical assumption on epsilon, which is certainly not optimal. This is what we get with our current techniques. So takes maybe a while to pass this inequality. It means epsilon can go to 0 like much faster than any inverse power of the log, but much slower than any power of mu. But this is what we can do currently. Then you get this convergence. You get the convergence of the partition function and the reduced density matrices towards those of this true Euclidean field theory in 2D. In fact, it's of some importance to note that this convergence, so I didn't talk about topologies. So this thing here is a density matrix. This is another density matrix. So you can ask about the topology of convergence, which is of some importance. And in fact, the convergence, so we prove convergence in terms of operator kernels. So you should regard these things as operator kernels like this one. We prove convergence in LP of this, or LR, let's say, of this function of 2p variables with optimal exponent r. Unfortunately, you can't prove convergence in L infinity or in the space of continuous functions, because these density matrices, as soon as you are in dimensions above 1, they are not continuous and they are not bounded. They have singularities. Whenever 2 such arguments coincide, for example, if x1 coincides with x1 tilde, this thing blows up. But there are instances where you would really like to set these arguments to be the same. For example, if you would like to compute moments of the mass of the field, or in the quantum world, if you would like to calculate the expected number of particles or the variance of the number of particles and so on, you would like to set 2 of these arguments to be the same. And you can't do that because you just get nonsense. You get something infinite. What you can do is to big order your correlation functions and your reduced density matrices. So here, you just put 2 dots here. You would take this whole monomial and you big order it. And this is a much more stable object. And you can, it's a very explicit calculation. You can do this calculation, and on the level of the kernels, it amounts to just subtracting terms involving the density, the correlation functions of the free field. So this is, in fact, the second big ordered correlation function. It looks like this. So you just take the combinations of lower order correlation functions and correlation functions of the free field. And this removes the divergences. And for this, you can prove convergence as continuous functions of these kernels. And in particular, this allows you to obtain convergence results for example, for the distribution of the centered number of particles. You can compute things like the correlation of the number of particles in this box and the number of particles in that box, and relate all of these things to correlation functions of this Euclidean field theory. Okay, So that's the main result. Let me say a few words about the proof. In fact, the rest of my time I would like to spend on the proof. Do I have, how is it, like 25 minutes or something like that? Is that...
Yeah, about, I mean, we started a couple of minutes late, so just go ahead.
Okay. So the basic approach of the proof, there are two steps. We pass via an intermediate step. And the intermediate step is a mean field type step, except you don't compare it to the, I mean, it's a step where you compare it to a modified non-local field theory with the interaction potential V. So that's what I explain here. So we replace this interaction, which is a limiting interaction, with the following intermediate interaction. And what is important is this thing here. So you replace this, which you can regard as being this term, forget the Wick orderings for now, with a delta function. So you don't take a delta function, you take your approximate delta function V epsilon. And now actually the Wick ordering is important, and that's the main source of headache. So you would like to Wick order this whole thing, but what is required for the proof to work is a Wick ordering of these individual ones, which is a lesser renormalization. I mean, this thing is more renormalized than this. And this alone will blow up. You can construct the field theory for this object, and you can send epsilon to 0, and this thing will blow up. It's not well defined in the limit epsilon tends to 0, so you have to manually subtract some counter terms, which are these ones here. So I have two parameters which are called tau epsilon and E epsilon. And this is again just a renormalization of the mass, and this is a renormalization of the energy. And in fact, they have explicit expressions, so I can give them here. They are not so important, but this is what you have to choose to make the whole thing work. So maybe the important thing is just to see that these things blow up. I mean, this is remember, g of x has a logarithmic singularity at the origin, and V epsilon tends to the delta function. So this thing blows up as epsilon tends to 0, and so does this. So this is our intermediate interaction, and so we will compare both theories to a field theory, a Euclidean field theory, with this interaction. That's the basic strategy. So there are two steps. The first step, as I said, is to compare. Let me talk only about the correlation functions or the reduced density matrices. So you compare the reduced density matrix of the true quantum interacting quantum gas to the correlation functions of this interacting field theory. So I use this superscript to denote the interaction of the field theory. I put in hats to emphasize that these things are the Wick-ordered correlation functions. So the proof works entirely on the level of the Wick-ordered correlation functions, these ones here. And I will say much more about this because this is a tricky step. And the basic strategy here, which I will explain in more detail in the next 15 minutes or so, is to do a quantitative analysis of a bosonic functional integral that we constructed last year. So this is sort of it's a rather pleasant way of defining a functional integral for Bose gases, and it turns out it's very amenable to analysis. So you can do analysis very well for reasons I'll explain, and in particular you can study rates of convergence and take you can include approximate delta functions, and you can still control things. Once you've done that, the second step is to compare then these two interacting field theories. So this one and that one. And this one is a purely field theoretic step. So we have no Bose gases at all. We just have two field theories in 2D. So it doesn't sound too scary. And one can do it basically in using three main ingredients, which I will not give too many details about. The first one is you again have to prove the integrability of this interacting factor with respect to this probability, with respect to the free field, and this has to be uniform in epsilon. And this can be done, in fact, basically by extending Nelson's original arguments to non-local interactions. It's a bit more annoying than so doing it for this interaction is in fact more annoying, a bit trickier than doing it for the original Nelson's interaction, but it can be done. Then you want to analyze the difference between these field theories, and it turns out it's sufficient to estimate just the L2 norm of this difference. So you take these two things, you calculate the L2 norm, you apply Bick's theorem, and then you have to apply some relatively elementary estimates using the green function. And then you can upgrade this L2 convergence to all sorts of other modes of convergence using hypercontractivity. If you're familiar with these things, it's basically, at least for this context, and I think almost all of its applications in quantum field theory and stochastic PDEs, I think it's really just a fancy word for applying Bick's theorem. I mean, you apply Bick's theorem and then you do a few, you do some combinatorics. You apply Bick's theorem and you do combinatorics. That's basically it. And then finally, if you want to get good control of these V-quartered correlation functions, you have to do an extra step, which involves a differential representation of these V-quartered correlation functions. I will not go into that, but it turns out they have a very, very beautiful representation in terms of differential operators, which is quite analogous to Maillevin calculus, if you're familiar with that. And starting from this representation, there are lots of estimates. There's a huge number of things you have to estimate, but none of them is particularly scary. And you can just go through them, and you will get this kind of strong control on the correlation functions. So this is a very brief summary of step 2. Let me now explain the setup of the step 1. So how does this functional integral work, and how can you do analysis on it? I will start with something that's completely non-rigorous, but it gives you a good intuition for where this functional integral comes from. In fact, this is relatively well known, this formal functional integral for the interacting Bose gas. What you can do is, if you want to derive this, I will tell you what it is. You can also rigorously. So I will give you the plan for the next 15 minutes. Is I will give you a formal functional integral for the Bose gas. I will tell you how to rewrite it in a way that can be made rigorous, and then how we apply it to our proof. In some sense, this is kind of sort of backward engineering, if you wish. This is a reverse engineered way of motivating this thing. A more direct way of doing that is you can take a Bose gas in a very simple setup, for example, bosons on a finite lattice or something. And then you can derive a functional integral. You can maybe discretize time and so on, and then you will arrive at these kinds of expressions. And this, in fact, has been done for many decades, and this is relatively well known. So let me summarize how this goes. You formulate the Bose gas as a field theory, again as a field theory, except now you have fields defined on space-time. So you have the same torus, and now you introduce time. And time is the compact interval 0 to nu. And you can think of this nu as a beta, if you wish. If I go back to my, I take e to the minus hn, and nu is the guy in front of here. So if you know something about functional integrals for bosons, you will know that the beta is always the length of the compact time direction. And you can think of this nu being the usual beta, inverse temperature. Okay, and formally, our functional integral is of the following form. So again, you have this. It's of this Gibbs form. This d phi is this formal Lebesgue measure on the space of space-time fields, and S is an action, and it's composed of the free action and the interaction. And the free action, so you integrate over space-time. You take this quadratic form of your field. You have the Laplacian, you have this chemical potential kappa. And the new thing is you have this time derivative. That's somehow the key feature in this, or the key new feature in this functional integral representation. So you differentiate your field in time. that's what you get. And the interaction is the one you would expect. So you integrate over time first, and then at the same time you integrate over two spatial variables, and your field will interact like this, as you would expect. This is all very nice. So you've rewritten your theory of Bose gases in terms of field theory, and the price you pay is quite severe. The first price is that you have a field on space-time instead of space, and that's okay. I mean, space-time is also fine. There's a much worse thing is this thing, yeah, because this is it's in fact anti-self-adjoint. So you have a field theory where even the free theory does not have a self-adjoint covariance. This is an anti-self-adjoint part. I mean, it's normal, these things commute, but it's not self-adjoint. Formally, you can compute then all of these quantities like the reduced density matrices, and they are just correlation functions of this field at time 0. This is a very nice little calculation one can do. Let me now formally explain at least why in the mean field limit you would expect to get this Euclidean field theory. So what we want to do is we want to send nu to 0 with this scaling lambda being nu squared. And in order to do that, it's convenient to parameterize. You see, nu is the length of this interval. If you want to take a limit, it's not nice to have integration bounds depending on your limiting parameter. So take I will just call tau, I will parameterize tau as nu times t. So that's what I do. I define a rescaled field in terms of a new variable t. I also rescale it by square root of nu, and I call this phi prime. And now t lives on the compact interval 0, 1. So then just by change of variables, s of phi is equal to s prime of phi prime. And you can, and here is my phi prime. So the interaction part is the same. And the free part is the same, except I integrate from 0 to 1, and I get a 1 over nu in front of the time derivative. And now what happens, at least formally, as you send nu to 0, this is just formally, it's just a stationary phase argument, right? You put this in the exponential, put an I in front of this delta t, and have a minus I in front, or, well, maybe not in front, but write delta t as minus I times delta t. I times delta t is self-adjoint, and then you have a minus I times the self-adjoint operator, which you multiply with a constant that blows up. You multiply with a factor that blows up. And this is, at least on a formal level, this is just a stationary phase argument, that the dominant contribution of this integral comes from the fields which are constants in time. So you would just kill this term, you would set time to be 0, and if you do that, you get exactly the Euclidean field theory. So this gives a nice heuristic argument for why you would expect the field theory to emerge from this kind of functional integral. Of course, this is all extremely formal, and what we would like to do is to make some mathematical sense out of this. And in fact, it's not so easy to make this thing rigorous. So even the free theory, taken literally, makes no sense. And it's not that it makes no sense because we are too stupid to make sense of it, and we as in mankind, it actually cannot make sense. So this thing, you can define it, you can discretize your space-time cube. It makes eminent sense. You can try to take the continuum limit, and this will never converge to a measure. This is a big distinction between finite and infinite dimensional Gaussian measures. If you take a finite dimensional Gaussian measure, you can have a non-self-adjoint covariance as long as its real part is positive. There's no issue whatsoever. It's perfectly fine. In infinite dimensions, if you have a covariance that's self-adjoint, that's also fine. You can construct your Gaussian measure in basically in any situation you wish. However, if you have a covariance which is non-self-adjoint, even if its real part is very nice, in general, this is not going to work, and this is the case here. Another very famous example of this phenomenon is the functional integral formulation of the propagator of quantum mechanics, right? So if you take e to the I t times Laplacian, If you do a big rotation, so if you get rid of the I, then this has a rigorous functional integral representation, which is just Brownian motion. Yet, if you include the I, this thing cannot arise from a Gaussian measure. This is sort of a no-go thing. And the same problem occurs here. And this, in fact, was proven by Cameron in the 60s, that no matter how you rescale and renormalize things, this thing cannot lead to a well-defined measure. The problem is that the oscillations from this thing are just too large. They become too large, they cannot be controlled. So there's no hope of assigning a measure to this thing. This will never be a measure. What you can do, however, you can be a bit more modest. You can say, well, we don't really need a measure. We just need a linear functional that acts on a sufficiently large set of functions so that we can define correlation functions. And this one can do. So this is an object. It's not a measure in the limit, but it does have well-defined correlation functions. And this point of view, in fact, this very functional integral formally is also the starting point of this epic program you're probably familiar with by Balaban, Feldman, Knara, Trubowitz, and others to establish Bose-Einstein condensation. And you start from this functional integral. They make sense of it by discretizing space and then using a coherent state functional integral, which works well for their purposes. As I will now explain, we somehow take a different path to making this functional integral rigorous. And our starting point is the following. So let me...
Sorry, can I maybe interrupt quickly? So their method wouldn't work in your context, or...
I think not. I mean, we didn't really try because we were not very optimistic. I mean, these things are never particularly easy. I think they have 2 or 3 papers just to construct this functional integral. So it's difficult. I mean, their construction is difficult.
So yours is going to be simpler.
Well, you know, I would say it's a bit simpler, but it's different. So it's suited for it's possibly suited for different tasks. So ours is very well suited for the task that we were interested in. I think it's conceptually maybe a bit more streamlined. It's perhaps technically it's perhaps maybe a bit less direct, but I think if you want to make it rigorous, it's maybe a bit easier.
Okay.
But I think one could reasonably object to this. So these are all subjective impressions. Sure. And I don't know also whether our functional integral would it's conceivable that this would also perhaps simplify some parts of the argument. But this is not. I mean, we haven't looked at that.
That would be interesting. Okay, thank you.
So the starting point is to do a Hubbard-Stratonovich transformation. So how does that work? You introduce a new Gaussian field, which is a real Gaussian field on space-time. So this is a field I call sigma. So it's a real field on space-time. And so the Gaussian measure I call eta, and it has the following covariance. It's a delta function in time, and it's v in space. So so it's white noise in time, and in fact, for the applications, if you recall, we will take this v to be an approximate delta function. So it's almost white noise. It's almost space-time white noise. It's fully white noise in time and almost white noise in space. Then what you can do is you can rewrite. So I will now start from these formal expressions that I wrote. I will try to rewrite them in terms of this Hubbard-Stratonovich representation. And I will try to arrive at expressions which can be made sense of rigorously. So for simplicity, let's just look at these the relative partition function. You can do similar things for reduced density matrices. So this is the thing we would like to understand. And now you do your Hubbard-Stratonovich transformation, which is nothing but a Fourier transformation of this interacting term. So I think many of you are familiar. If not, you can do this as an exercise. It just uses the fact that the Fourier transform of e to the, you just represent e to the minus x squared in terms of its Fourier transform. and then you get an extra factor. So you reduce the interaction, the quartic interaction, to a quadratic term, which multiplies the field phi over which you integrate, the field sigma over which you integrate. Okay, so this is a simple algebraic transformation using this covariance. If you haven't done this before, it's maybe not immediately obvious that this covariance is the right one, but you can do this as a little exercise, and this is what you find out if you do this Fourier transformation carefully. You can pull it out because this field sigma only appears in the numerator, so the denominator is what it is, and we just get this. So you get this quotient of these two integrals, and now they are, at least formally, they are Gaussian integrals. You get a quotient of two Gaussian integrals, and then you have to integrate over this field. So let's just give a name to this operator appearing in these exponents. So let me call this guy here K, and it has an argument U, which can be a generic function. In fact, it has to be maybe something a bit more general. Maybe it has to be even a distribution, because I might want U to be white noise. But let's ignore these analytical issues for now. So this K of U is the following operator. It's the derivative in time, it's Laplacian in space, and then I add this field, which can be a distribution. And that I can just rewrite the formula I had before in the following form. It's a quotient of these two things. And now I can do what I've learned in basic Gaussian integration. I can integrate, I can perform this Gaussian integral. And this gives me a determinant. It gives me a ratio of determinants for two different arguments of this K. So let me summarize. I've shown that this relative partition function is given by the integral over this auxiliary Gaussian field of this quantity e to the f1 of sigma, where f1 is the logarithm of this ratio of determinants. And you can express a logarithm of a ratio of determinants as a trace of differences of logarithms. Here it is. And then it's very convenient to use an integral representation of the logarithm. This is a calculus exercise that you can write these things as follows. So this f1, in other words, is an integral over t going from 0 to infinity of resolvents of this operator K. Then what you would like to do is to write these resolvents or green functions in a slightly more explicit way. And this we do by introducing a propagator of the heat flow. So let me define W. So W is a propagator going from tau. I always go from right to left. So going from tau tilde to time tau. It depends on your function U, which I remind you depends on time. So my U here was a function on space time. Now, however, my t goes or my tau is allowed to go from 0 to infinity. So when I introduce this U, I take the tau, the new periodic time. So if I take times larger than nu, I just fold everything back to the interval 0 tau. And I define this W to be the propagator of this heat equation. So it's a pretty benign heat equation, except I have this U in front. Well, benign, I mean, U might be very singular, but otherwise it's a normal heat equation. Then I summarize in blue. What I summarize in blue will be the rigorous construction of this functional integral. So this is our way of constructing this formal functional integral in a way that's completely rigorous. Then you can do, this is an amusing little computation that you can do. It's just algebra, basically, at least if your U is nice, that the green function of this operator K, so here is my operator K. The green function, so what is it? It's a function acting on space-time. So it's a green function. I will need two space-time coordinates, and I write it like this. So the first space-time coordinate is tau tilde x tilde, and the second space-time coordinate is tau x. This can be written as a sum, such a periodic sum. So R is going to be a multiple of nu, and and you basically sum over all r's for which this thing makes sense. So it's a heat equation you can't run, you can never run it backwards. So this time has to be larger than that time. That's just this indicator function here. So this is an identity. And these propagators are all mathematically well defined, and then the claim is that you just plug this into the expression we had before, and that's your rigorous construction of your functional integral. Okay, so these we already had before. There's nothing new. I just take them on this page to summarize the whole construction. And then these integrals, you see this is a trace, so you will set tau tilde to be equal to tau, x tilde to be equal to x. In this expression, you integrate over x and tau, and that's what you get. So that's how the construction works. I will explain in a few slides how to actually deal with this W. But maybe before that, let me just remark that these you can do exactly the same thing for the correlation functions, and you can prove that if you start from the correlation functions of this formal field theory, you get exactly the reduced density matrices.
So you have officially 2 more minutes, but you can carry on a bit longer.
Okay, no, I will not take more than 2 minutes.
Okay.
Let me make 2 final concluding remarks. One is how to Wick order. Wick ordering enters this whole thing in a very pleasant way. This was my F1. Here it is. It turns out that Wick ordering, this is a computation you can do. It's like a page or so. So the energy renormalization is easy. It commutes with everything. So you can just, you can just put it in as you wish. The mass renormalization that you introduce from the Wick ordering, it turns out you can express it exactly in this form. And now if you see, so this is what you have to subtract from your F1. And if you compare this to this expression, you see that this is just cancels precisely the term you get if you start doing resolvent expansions in the field sigma, right? If you do a resolvent expansion, in the field sigma, then the first order term you get is exactly this one with the opposite sign. So that's killed, which means that this cancels the first order term in this difference, and this is crucial in ensuring better integrability in both space and time, space and time in the trace. Okay, so that's to give you an idea of what to do with this Wick ordering. Now, how to prove convergence, I will not go into details. Basically, what you can do is you can take a representation inspired by Szymanczyk for the Euclidean field theory. You can derive a very similar representation, again using a Hubbard-Stratonovich transformation. It works in the same way, except it's much easier. You have no time direction. The key is that so you get a new field psi, and the key is you can couple these fields sigma, which I had, which was a field on space-time, the auxiliary field on space-time, and psi is my field, my spatial field for the field theory, and you can couple them as follows. So this is a simple distributional identity, and in fact I can choose my field psi that I use for the Euclidean field theory as given by the following expression. And then I can combine expressions, take differences, and it turns out that these kinds of sums that we saw before, you can view them as Riemann sums. And if you take limits, if you start taking limits, they converge to integrals, which are exactly the integrals you get from this field theory. So essentially, at the very core, the very end, our analysis amounts to proving convergence of Riemann sums. You can view it like that. Let me just conclude. Of course, I mean, there are, as you might imagine, the analytical difficulties arising mainly from these issues that this sigma is white noise in T and also in X, because we are going to a delta function. So the analysis is somewhat involved, but I tried to explain the main algebra. And finally, to conclude in the last 30 seconds or so, let me just say how at least to make you believe that this analysis can be done. And it in fact can be done in a very pleasant way thanks to the Feynman-Katz formula. That's somehow our key gift in this whole business, that we would write the propagate. Let me go back to this heat equation here. So you take this heat equation, and this is a textbook example of something that can be expressed in terms of the Feynman-Katz formula, right? So this is the notation I use. So this is the Brownian bridge measure. This W, again, going from, now it's going from x tilde at time t tilde to the point x at time tau, sorry, tau tilde to tau. This is my Brownian path, and I just put this weight, which corresponds to my distribution mu. And we can rewrite all the expressions in terms of this Feynman-Katz formula, and then it amounts to basically an analysis of Brownian bridges. And Brownian bridges are very, very nice, very well understood objects. We have extremely good estimates on path properties and distributions and everything. So it's thanks to these kinds of formulas that this analysis can be done. Okay, good. I think, yeah, my time is anyway up, so I will stop here, and thank you for your attention.
Thank you. Thank you very much for the very nice talk. So we can all Antti in this way or the other. Yeah, so the floor is now open for questions. So the easiest way is just go ahead and unmute yourself and ask a question.
May I?
Yes, of course.
Hi, Antti. Thank you for
the
beautiful
Michael.
talk. Thank you for the beautiful talk. I missed the first minute, so perhaps you answered it. Do I understand correctly that the discussion is in a finite volume?
Yes, that's right. Yeah. There's no, we don't look at the infinite volume at all. This is we work on this torus. Yeah.
Thank you.
We have another paper where we think a bit about the infinite volume limit. In fact, of course, it's a very interesting question. It's also an interesting question for these techniques. What we do have some results in infinite volume. I mean, which are perhaps not very surprising. We use cluster expansions at a sufficiently weak coupling. But in order to make these cluster expansions work, we in fact use a different representation. We don't use this functional integral representation. We use a representation using random loops, a la Ginibre and Simanczyk, which is very convenient for doing cluster expansions. And it's conceivable, we haven't really thought about it, that this kind of that you could also do cluster expansions using this kind of functional integral representation.
Mm-hmm. Thank you.
Thank you. Anyone else?
So could I just ask a question about, so the potential is repulsive. What are the problems exactly with having also a negative part? I mean, some attraction, the potential.
Yeah, it's a good question. There's a very obvious problem. Is if you just take this measure and you have a potential. So here it is. Let's look at it here. So this is my quadratic part. If this thing has even one direction, so a one-dimensional subspace where it is negative, then this thing will blow up immediately, because you will have, in the exponential, you will have quartic growth in one direction, and the only thing that can control this quartic growth is quadratic decay from this S0. So that's never going to work. So if you have even a single direction where your interaction is attractive, you're dead from the start. But it doesn't mean you have to give up immediately. So this in fact has been considered a lot in the literature, these questions, and they are very interesting. What you have to do is you have to one way to deal with this is you truncate in the field. So you say that you consider the field only within a ball of a certain radius. And this works very well in 1D, kind of trivial. I mean, 1D, everything is sort of trivial, right? So this obviously works in 1D. In 2D, this is already a very interesting and not easy question. The truncating in the mass doesn't really have a meaning. You would have to truncate in the weak-ordered mass. And there's work starting, I think, from Lebowitz, Rose, and Speer on these questions, and there have been quite a lot of other works as well. And it's delicate, and there are, I mean, even in 2D, depending on your assumptions and your interaction, there are cases where even truncating in the big ordered mass cannot lead to well-defined theories. So it's a delicate question.
Thank you.
Okay, thank you.
There's also another question from the chat. Do you think the results in focusing measures with energy norm cutoffs will be of relevance here? So
No, yeah, you answered it, Antti.
Please go ahead.
Yeah, thank you.
Oh, okay.
Yeah.
Yes. Yeah, okay, Trish, hi. Yes.
Hello.
That's right. Yeah.
Very good. Any other questions?
Hi, Antti. Thanks a lot for a very nice talk. It's
Hi,
Michael.
Mike. Hi.
So
Hi.
I would like to elaborate a little bit on Daniel's question. Can you have a negative piece such that you don't have a negative direction? Negative direction corresponds to the negative eigenvalue for your some kind of
so you're asking, can you have I mean, well, this is not this doesn't really have eigenvalues, right? This quartic interaction. I guess it's if you just have a one-dimensional subspace such that if you restrict this function to that one-dimensional subspace, it tends to minus infinity.
Right, but I can look at this as kind of a roughly as a quadratic form. Of course, it is not quadratic as a pseudo quadratic form, and then look at the operator inside of it and look at the spectrum. And the spectrum is purely positive. You don't have a negative direction. Nevertheless, I can imagine adding a negative piece to this operator, so its potential is negative, but the spectrum is still positive.
I'm not sure I understand. So how do you make an operator out of this?
Okay, I take the full action,
Yes.
and I write it as a quadratic form with a, say, phi operator phi, but operator depends on phi too.
Oh, I see. Okay. I think it's not important that you have. I think you will have problems even if you don't have a negative eigenvalue. I think if you just have some direction, if you have any direction, even if it's not an eigenspace, where this thing becomes negative. In fact, if you have any, if there exists a phi such that this thing is negative, even forget about eigenspaces. Find a single phi where this thing is negative, you're dead.
Yeah, so I would like to make this form, this S, to be strictly positive, nevertheless with a negative piece inside. Okay, so anyway, this becomes a little bit technical, but that's what that's kind of a direction I was heading at.
I think so. Okay, my impression is that you would, if you have such an interaction, then without some kind of cutoff, then you would be in trouble. Because you can just, formally, you can just consider the one-dimensional. I mean, if you view this as, as an integral of infinite dimensional space, you can just take the one-dimensional integral in that direction. And this thing is homogeneous. So you will have quartic growth tending to minus infinity. And this will never be compensated by any kind of quadratic decay you get from this.
Okay, thank you.
Anyone else?
I have a technical question. At the last moment, at the last stage, when you work with traces, do you need to control convergences and estimates in the trace norm topology?
That is it's a very good question. We don't need to. We would, in fact, we would have liked to. And we thought about this, but we were unable to do so. I'm not sure if these things converge in trace norm topology. If I were to guess, I would say yes. These kinds of things, or these kinds of convergences here. But we couldn't do that. So what somehow comes naturally out of this formalism is it's a formalism that functions, that operates on the level of the kernels. Everything is on the level of the kernels. We use these Brownian bridges. We get expressions which are really on the level of the kernels. And so these LP norms are very natural. And what comes out very naturally is the L infinity norm control. And the main application, at least as far as we understand, the main physics application of getting trace norm convergence would be to control the number of particles. And this can be equivalently done if you get L infinity norm convergence. So it was good enough for us for all of the applications that you would be interested in. And these are two notions of convergence, which are, as far as I know, are not in any relation. So one doesn't imply the other. But as you know, if you are working with operator kernels, it's extremely unpleasant and difficult to get any kind of control on the trace norm, and we couldn't do that.
Thank you.
Thank you. Any more questions? So maybe just a very general question. So what's the scope of application of your methods? So would it apply also to other interactions, other problems? So are there some ideas for generalization?
Yeah, there are ideas for generalization there are, I suppose, first analytical generalizations. By the way, I apologize if I don't know if you can hear some background noise.
No worries.
Okay, if you can hear it, I'm sorry about that. So analytical extensions, obviously, in the sense that you can make your potentials, more singular. You can ask questions of the kind of the one that I discussed now, and you can change dimensions. You can change rates of convergence and so on. Beyond that, I think one should be able to include attractive interactions. Sorry, as we discussed. Then you would have to truncate appropriately. Mm-hmm. Considering, if you wish, perhaps, different types of interactions, perhaps, three-body interactions might be conceivable. And the basic approach, we haven't explored this much, but the basic approach in principle should also be applicable to fermions.
Oh, okay. Oh, that's nice.
This is kind of, let's say, a more distant thing, but I think it's in principle, there's, all of the algebra that I explained should go through fermions as well. And then the question is, what kind of analysis can you do on this?
Okay. Yeah, thank you. Right. Anyone else? I think we're good. There was a lot of questions, so maybe let's thank Antti again for this very nice talk.
Thank you.